In this video, I want to take a look at the concept of coordinates with respect to a basis. Now, at the end of the previous video, we had a theorem about the uniqueness of basis representation. That is, if you have a set of vectors, v1 up to vn, that is a basis for a vector space V, then any vector in the vector space can be written as a linear combination of those in a unique way. There's only one way to do it. Okay, and because of that uniqueness, that there's only one set of coefficients here, C1, C2, to Cn, that will make this work and add up to V, then we can define these numbers as, we can use these numbers to define a couple of concepts here. The first is that we're going to call, so you got a basis, you got V being this linear combination of those basis elements, then the coefficients are called the coordinates of V relative to the basis S. And we create a vector in Rn with the coefficients written as the components of the vector in Rn. And this is called the coordinate vector of V relative to the basis S. We denote it with the following notation. You put the vector in parentheses and a subscript of the basis that you're using, right? And that's this C1 up to Cn. Now, one thing I need to point out here is that the notation for sets generally is not, I mean, this is a list of things, and generally that list of things can be written in any order. It is considered the same set. Okay? As long as it's got the same things in it, I don't care what order they are in, it's the same set. However, when I'm assigning these coordinate vectors, I need to make sure that I know the order, because I'm writing an ordered list of numbers, C1, C2 up to Cn. So if I were to switch some of these vectors around, I might have to switch some of these coordinates around. We'll see an example of that below. But so even though the notation is set notation here, which generally order is not important, I'm numbering the elements so that there is an order. There's V1, there's vector 2, there's vector 3, there's vector up to n, right? And notice this is a finite set. Here's an example. In R2, I'm going to let the set B be these two vectors, 1, 2, and negative 3, 4. Now, it might take a little bit of proving, but that is a basis. They are linearly independent. Well, certainly it's easy enough to see they're linearly independent because one is not a scalar multiple of the other. And they span all of R2. A little less than obvious, perhaps, but it's you can check that. Well, I'll have a way of seeing it here in a moment. So I want to take a look at this vector, negative 6, negative 2, and I want to find the component vector of V with respect to this basis B. Just a little bit of notation here. I'm using B as basis instead of S like we had up here. I generally save S's to represent the standard basis. So like in R2, that would be 1, 0, and 0, 1 would be the standard basis. And if it's something else, I usually use a different letter. I think S is just being used as set, but we're making that set be a basis, so I just use a B for basis. Anyway, in order to find the component vector here, I need to realize, how do I make this vector be a linear combination of those two? So I need to find two numbers, a and b, so that this vector is a times the first one plus b times the second one. And well, one vector equation in R2 is two real number equations. And so first component, the negative 6, has to equal a minus 3b. That's this first equation. And then the second component, the 2, has to equal 2a plus 4b. So there it is. There's a system of two equations and two unknowns. Once you've chosen your favorite method of solving, you'll find that a equals negative 3 and b equals 1. We can just double check that here. If you plug a negative 3 in for a and a 1 in for b, certainly that one's true. And then negative 6 plus 4 is negative 2. So yeah, that works. All right. And so the component vector of V with respect to the basis B is negative 3, 1. Negative 3 is the coefficient that goes in front of the 1, 2. The 1 is the coefficient that goes in front of the negative 3, 4. Okay. Now, let's take a look at the picture of this. So I have here the two vectors, 1, 2, and negative 3, 4. And from that, I essentially generate a coordinate system, right? In the background, you can see the standard coordinate system, which is based on the standard unit vectors, right? 1, 0, and 0, 1 would be those two vectors. And then I've got a grid based on, move over 1 in the direction of the first basis vector, and then draw a line in the direction of the other one, and then move over 2 and draw that line, or move in the direction of the second basis vector and draw a line in the direction of the first basis vector. So you get this grid of squares for the unit, the standard unit vectors there for the basis. But with these two as the basis, my grid becomes a bunch of parallelograms. Right? But it really lets me see what's going on here. Because when I talked about the point negative 6, negative 2, that's with respect to the usual basis, right? So go negative 6, negative 2. That's this point right here. Right? This point right here, which happens to be nicely on that grid of blue lines. But what I see is that if I go in the direction of this vector, and then 1, 2, 3 in the opposite direction of that vector, so maybe I should do it the other way first, go this vector, go backwards 1, 2, 3, and then forward in the direction of the second vector, it gets to that point. So on that blue grid, the coordinates of this point are negative 3, 1, because I go negative 3 in the direction of my first basis element, and then 1 in the direction of the second basis element. And in this way, you can see what any one of these points are with respect to that basis. For instance, it looks like this point right here, which normally I would call 2.5, 0, right? That 2.5, 0 is right here. It looks like what I need to do is go 1 in the direction of my first basis element, and then negative 0.5 in the direction of the second basis element. So the coordinates of the point 2.5, 0, with respect to the other basis, the blue basis here, would be 1, negative 0.5. And this is really the way you should think about these coordinates with respect to different bases, is that the basis itself sets up a grid of parallelograms, well, when you have just two of them, but it sets up its own coordinate system, and then you attach coordinates appropriately, right, for wherever you want to be. Notice that the order is important here, that if I had listed my vectors the other way, listed this one first and that one second, then the coordinate vector with respect to that basis, I'm calling it B2, would be 1, negative 3 instead of negative 3, 1, because this is corresponding to the first basis element. It's the coefficient for the first basis element, and this is the coefficient for the second one. So this would say go 1 in the direction of your first and negative 3 in the second. Okay. So again, although the set notation really doesn't imply an order, with respect to this process, we need to impose an order, right? And so the way they're listed is generally the order that we take. Right? Let's do an example in another vector space. How about M22? So matrices that are 2 by 2. We saw in the previous video that these four vectors make up the standard basis, and I've written them in the order I want. 1, 2, 3, 4. And now I'm going to take any vector in M22, which vectors, of course, are just matrices, 2 by 2 matrices. And I claim that I can write this 2 by 2 matrix as A times this first one, plus B times the second one, plus C times the third one, plus D times the fourth one. And so the coordinate vector of this matrix with respect to that basis is A, B, C, D, that vector. That's in R4, right? This is a list of 4 numbers, and so that's in R4. It's curious that there's a pairing now between matrices that are 2 by 2 and R4. In the same way, we could do something like this, where I'm going to look at polynomials, second degree polynomials, or degree 2 or less, right? Where my basis is the standard basis, 1, x, and x squared. And I'm going to pick a random polynomial, a random quadratic polynomial, 3x squared minus x plus 5. And I say, what is that vector? Of course, in P2, the vectors are polynomials, right? So that vector, with respect to this basis, what are the components? Well, because of the order, I'm doing the constant, the linear, and the quadratic terms. So the constant term here is 5, the linear term is -1, and the squared term is 3. Right? My claim is that this polynomial are these coefficients times those vectors added up. Right? And in this way, we can actually see a correspondence between P2 and R3. Right? For every polynomial, every second degree polynomial, you have a corresponding point in R3. Likewise, for every point in R3, you can use them as coefficients to multiply by those 1, x, and x squared, add them up to create a polynomial. So you have a one-to-one correspondence, actually, between P2 and R3. And this is actually a very powerful tool when we get into a little bit higher level of linear algebra. There's this notion called an isomorphism. Whatever. It's a transformation from one vector space to another that preserves a lot of properties, right? It's a one-to-one transformation. It's an on-to, so that everything here gets mapped. So everything in the range space gets mapped by something in the domain space. Anyway, and it preserves linear properties, right? It's these things called isomorphisms, essentially saying that this vector space is exactly the same as that vector space. You're just calling the things something different. And it turns out that this coordinate transformation is what's known as an isomorphism, essentially saying that P2 and R3 are essentially indistinguishable. They're the same thing. Likewise up here, M22 is indistinguishable from R4. Now, we're not going to be doing isomorphisms in this class, but I want to point that out, that this really is important stuff. One of the things I think it does is it just makes the notation cleaner. That is, rather than looking at these things, you might as well be looking at stuff in R4. Rather than looking at polynomials, you might as well be looking at stuff in R3. Second degree polynomials to R3. Yes, there's my note. The process of making coordinate vectors is a transformation from V to Rn. It is, in fact, an isomorphism. Anyway. And another note, we've really been doing this for a while already. Just think about what we do in R3. Any physicists or engineers generally write their vectors in terms of linear combinations of I, j, and k, where I is 1, 0, 0, and j is 0, 1, 0, and k is 0, 0, 1, right? And so you have a vector, ai plus bj plus ck, and me as a mathematician, I would much rather write it as a comma b comma c, write it as a list of numbers rather than as a linear combination of basis vectors. It's the same process. You have a vector, you can write it as a linear combination of basis vectors, or you can write it as a list of the corresponding what are these things? Coefficients? Yeah, corresponding coefficients. So there's a bunch of them to do in the homework, to just give it a try, to rewrite a vector in terms of another basis, and then represent that as a coordinate vector. So have fun.